Welcome. Today we will be discussing the review part of algebra as well as matrices for preparation of the rest of the class for Math 150 Plane Trigonometry. For the algebra review, we will be going over system of equations, some common rules, exponents, quadratic formula, and factoring. So as a brief reminder, to find an equation, we'll first start off with an example of 8x minus 2 equals 5x minus 8. We can combine like terms by subtracting 5x to each side. 8x minus 5x, that gives us 3x. And we're going to set this equal to, we have a negative 2 and a negative 8. Let's add 2 to the other side. Negative 8 plus 2 is negative 6. Divide by 3, divide by 3, and we get x equals negative 2. So we had one variable being x, one equation, and we were able to solve it. For a system of equations, we can have an example like x, y, or sorry, I didn't say system equation, I should say multivariable equation. X, y is equal to x plus 2y. Now here we can solve for x or we can solve for y. So we're going to break this up into two cases. So first we're going to solve for x. And what we can do is subtract x to the other side to get xy minus x equals 2y. And then we can factor out this x. X times y minus 1 is equal to 2y. And now we can divide by y minus 1 to get x is equal to 2y over y minus 1. Now, something to note, we have a division here. So this only works when y does not equal 1. Otherwise, we would divide by 0, and that would be a problem. So we solved x in terms of y when y does not equal 1. If y were to equal 1, we'd have to come back to this equation and figure out what x is. And that is if there's a solution to it. So next one we have, we're going to solve it for y. When we solve for y, we can subtract by 2y, so we get xy minus 2y is equal to x. We can factor out a y times x minus 2 is equal to x. And we can divide by x minus 2, so we get y is equal to x divided by x minus 2. And this is when x does not equal 2. Because again, we would divide by 0. And we can see that if x were to equal 2, we would run into issues when we actually try to plug into the equation. Similarly, if y would equal 1. So this equation will hold as long as x does not equal 2 and y does not equal 1. Okay. So Now, let's try to solve 3 over t is equal to 7/9. Since we have 3 over t, we can assume that t does not equal 0, because otherwise we're already starting off on the wrong foot. And we're going to do cross multiplication. So we're going to times 7, or t times 7, and 9 times 3. 9 times 3, that is 27, is equal to 7t. Divide by 7, and we have t is equal to 27/7. Note, leave your answer in this form. Don't make a mixed number. And we can look at the factors to try and reduce. And 27 doesn't have 7 as a factor, so we can't reduce the fraction further. Okay. Now, another bit of rules is x plus y squared. When I go through that, I can imagine that this is x plus y times x plus y. So what the square is touching, it's touching the parentheses, so it's this quantity times itself. So now I do FOIL, or I prefer the term double distributive, meaning that I distribute the x and then I distribute the y. And it'll look something like this. We'll have x times x, which is x squared, x times y, so we're going to add x, y. Now we're going to distribute the y times x, so that's yx, and y times y, and that's y squared. Now, multiplication is commutative, meaning that we can swap the x and the y, or the y and the x. So typically we'll write this as x squared plus xy plus xy plus y squared. Now we have 2 xy's. So we can combine like terms. And finally, we have x plus y squared is equal to x squared plus 2xy plus y squared. Now, for the x minus y squared, we'll follow the same sort of path. We'll have x minus y times x minus y. This is equal to, we have x squared minus xy minus xy plus y squared. How do we get this? X times x is x squared. X times negative y, that is negative xy. Negative y times x, that is negative xy. And negative y times negative y, and negative times negative is a positive. So we get positive y squared because we have 2 y's being multiplied by each other. So finally we have x plus y, or sorry, x minus y squared is equal to x squared minus 2xy plus y squared. These are the rules that you are expected to know. Keep in mind at any point in this video, if I say something that you don't understand fully or you want to explore more, please talk to me during office hours. As a reminder, I will be available. They're posted on the Canvas page, and or send me an email. Now, expanding some of these rules a little bit more, we have this. X minus y times x plus y. We do double distributive and we get x squared plus xy. That's when I distribute the x. When I distribute the negative y, I get negative xy minus y squared. Xy and negative xy, when I add them together, they cancel out. And so I'm left with x minus y times x plus y is equal to x squared minus y squared. And remember that multiplication is commutative. So we have x plus y times x minus y, and we'll get the same thing. Now, I say it's commutative. It's commutative in the real sense, meaning that I can switch any of the two multiplications and it still works. Much of the same with addition. If I switch 1 plus 4, that's 5, and 4 plus 1 is 5. However, 1 minus 4 is negative 3, and 4 minus 1 is 3. That's not commutative. It's not the same thing. So with multiplication and addition, you can swap any of those around. And with multiplication and division, you have to be careful with it. So continuing on, let's talk about power rules. So we have x to the n is equal to x times whole bunch of x's. How many of them? N times. We're saying that we have n copies of an x. So if I have x to the 14th, that means I'm timesing whatever I have for an x 14 times. As you can imagine, that can get really big really fast. Or if it's less than 1, like 0.5, that's going to get really small really fast. We also have x m plus n is equal to xm times xn. So if I have like 2 to the 3rd power times 2 to the 2nd power, that's the same as 2 to the 5th power. I can just add the exponents together. And we can see this more clearly with this being like x times a bunch of x's. This is m times. And then we're just going to times that, this whole thing, we're going to times it by x times x times x n times. And we can just add these together because how many times do I add times x by itself? Well, m plus n. Kind of the same thing when I'm multiplying. If I have 3x, I'm adding x to itself 3 times. Okay. We have x m to the n equals x m times n. Meaning, if I have x to some power and I raise it to another power, whatever the power is touching, I'm multiplying it. So an easier example would be x squared cubed. The cube is touching the parentheses, meaning that I have x squared times x squared times x squared. Well, that now looks like this rule. We add them together, so we have 2 plus 2 plus 2. Well, that is 6. Well, that's the same thing as 2 times 3. So you might notice I could switch these. If I had x cubed and I squared that quantity, then I have x cubed times x cubed. Well, now I have 3 plus 3. That's x to the 6th because I add the 3's together and I get the same result. So now you might ask, well, what if I have x to the m divided by x to the n? Well, I have x times a bunch of other x's, m times divided by x times a bunch of x's, n times, and so I can cancel a bunch of x's. So whichever one's bigger, that's the one that wins. And so I can rewrite this as x m minus n, because let's say there's more m's than x's, or there's m is larger than n. So I would have more x's in the numerator than I do in the denominator, meaning that I'm going to get a positive number here. And that makes sense. What if I get a negative number? Well, x to the negative m is equal to 1 over x m. So if it's a negative exponent, it goes into the denominator. This is when we're working with variables. When we're working with functions, it can be a bit different, because it could stand for the inverse function. So then another thing I want to touch on is x to the 0 power. That is going to be defined as 1. So I have no copies of something. I'm just going to times it by 1. Okay? Because 1 times anything is itself. And so you can think of this as like it contributes nothing to whatever it's times by. Okay. So a quick reminder of the rules. I'm going to box them in. That these are aspects that we expect you to know. And if you don't know any of these aspects, please, or any of these rules, please come to office hours or reach out to me via email, and we can discuss this and hopefully be able to reach an understanding quickly so that you don't fall behind in the course. All right. Now that you had some time to look at this, I'm going to go over some more rules, namely square roots. So the square root is, you can think of it as it undoes a square, but we're going to be more general with it. So if I just take the regular square root of a number, I'm saying that this is the principal square root. So if I don't define that I want the positive and negative, I'm saying that I just want the positive answer. So if I just say square root of 4, you're not wrong to have plus or minus 2. However, if I want the principal square root, I say that the square root of 4 is equal to 2, and this one is the principal root. Yeah, and where this has both of them. Now, if I've used this in the sense of that if I don't have a 2 here, so if I don't have a 2 here, I kind of do, but we omit it because when I don't have a number there, I'm assuming that it's a square root. And so this is really equivalent to x to the 1/2. And this 1/2 notation, you can think of that it undoes a square. So if I was to square this, you would see that by my previous problem, I'd have 1/2 times 2. Well, that's x. 1/2 times 2 is just x to the first. And that's just one copy of x, that's itself. So whenever I see a square root without a 2, you can think of that it undoes a square. Now, if I see a cubic root, I'm going to attach a 3 here. It undoes a cube. So if I have this being cubed, I can think of this as x to the 1/3 times, or to the 3rd power. 1/3 times 3 is 1. That's x to the first. That equals x. Okay. So how you can think about that is we have the index. That's the number that goes in this box here. If the box is empty, it's a 2. And then we have this is called the radical. And here, the number inside is called the radicand. So you might hear online, if you see a different lecture video from another instructor or another source, you might hear a radical 2. We're not saying that that we're in the 70s and that's an amazing 2. No, it's underneath the square root. So if I see n square root x, I can think of that as x to the 1/n power. Okay. There is one caveat to this that I want to make mention, and that is, let's do both of these steps, but with a -1. So first I'm going to do the cubic root of -1. And I'll find that if I do this, what's something times -1 that can get 1 3 times, or -1? I have times it by itself 3 times, -1. So if I'm going to undo that, well, my cubic root of -1 is -1. Okay. Well, what is the square root of -1? Some of you might be going, I don't know, we always said that that was undefined. Some of you might be going, oh, I remember this weird thing called I. Well, technically it's I, but for right now, we're going to say that it's undefined. It's not defined as a real number, it's an imaginary number or complex number. More on that in a future video, but not for a little while. So the point of this is when I have this equation here, I fibbed a little bit that the square root of x squared is x. What I really should be careful about here is that what I wrote here, this is true when x is greater than or equal to 0, I have this property. If I flipped it around and I put the 2 inside here, so I squared it first, then I make sure that I don't have a negative number, and then I square root it, I'm going to get x, but I'll get the absolute value of x. So if I see x squared and I take the square root, I get the absolute value of x, which what this means is that it equals x if x is greater than or equal to 0, and it equals negative x if x is less than 0. Meaning, if it was positive, it stays positive. If it was negative, I make it a positive. Why? Because I'm taking the principal square root of this number here that I'm taking a square of. So if it was negative, it's not positive, and if it was positive, it stays positive. Okay. So what are some properties with the square root, you might ask? Well, it behaves much like a exponent. That's because it kind of is an exponent, as I wrote before. So if I have the nth root of a number that, and I times it by or I raise it to the n power, that basically gets me x, and this caveat is when I have n is, as I talked before with that whole squared thing, when n is odd, I have that. But if n is even, then x must be greater than or equal to 0 for this to work in general. And if I flip it around, if it's odd, it stays the exact same way. So when n is odd, I get this as well as nth root of x to the n equals x. However, when n is even, I will get, when n is even, we have the nth root of x to the n is equal to the absolute values of x. This is a technicality. As you work with it, you become more comfortable with it. Okay. So what about the nth root of two numbers? Well, we can split that much like we could exponents and have the nth root of x times the nth root of y. And same thing if we have division. If we have the nth root of x divided by y, that equals the nth root of x divided by the nth root of y. So example of this working, we could see the nth root of, actually, let's do the square root of 18 over 175. My first step would be to split the square root. So I have square root 18 over square root 175. And now I want to find powers that are perfect squares in here. So I know 9 times 2 is 18. So I have 9 times 2. I'm going to put that underneath the square root. Divided by 125. Well, I can guess that 25 is in there. And with a little bit of computation, I can see that 25 times 7 is equal to 125, or 175, I should say. So now we split the square root again, and we have square root 9 times square root 2 all over square root 25 times square root 7. And for completion, we have 9 is the same as 3 squared times square root 2 over square root 25 is the same as 5 squared times square root 7. And so the square cancels out with the square root. So we get 3 times square root 2 all over 5 times square root 7, and that would be our final answer. Some of you might be going, wait, I was taught rationalization. That is a-okay too. I am fine with this answer. The grader should be fine with this answer. If not, I will send out an email. And if we want to rationalize, all we have to do is times by square root 7 over square root 7. Square root 7 times square root 7, that is 7, because we have square root 7 squared. So we have 7 times 5, that is 35. That's in the denominator. And the numerator, we have square root 2 times square root 7. So we can combine that for square root 2 times 7, all underneath the radical. And so 2 times 7 is 14, so we're going to have a square root of 14. What's left outside is a 3. And so this is an equivalent answer that would receive full marks. Okay. The last bit that I want to cover is quadratics for the algebra part of the review. So the general form of a quadratic equation is ax squared plus bx plus c. That is a quadratic expression. Typically, we'll set it equal to 0. And what this does is we're going to have a parabola. And we want to find the roots. We want to find where it hits the x-axis. That's the most common usage of this. And so we have the quadratic formula. X equals negative b plus or minus the square root, b squared minus 4ac all over 2a. If you do not know this, or you're wondering on how we made this and understand this, talk to me during office hours. I would love to go into this and we can really dive into details and make you very proficient on this equation. Because this equation is old faithful. It will get you exactly what you want to know. It'll give you a real solution. It'll give you a complex solution. Typically, we're only interested in the real solution, and it'll tell us if there's no real solution. So it's very, very useful. And so an example of this would be if I had 2x squared minus 12x minus 5 equals 0. I could write this into the quadratic equation, and here's my a. This is my a. This is my b. And this is my c. Keep in mind my a is 2, my b is negative 12, and my c is negative 5. We plug this into the quadratic formula, and we get x is equal to negative b. So negative 12 is positive 12. plus or minus the square root, b squared, so negative 12 squared, minus 4a, which is 2, c, which is negative 5, all over 2 times a, which is 2. Okay. And so now this is equivalent to 12 plus or minus square root 144, that's negative 12 squared, plus, or we have negative 5 times 2, that is negative 10, times negative 4, so we have positive 40, all over 2 times 2, which is 4. So we have 12 plus or minus the square root of 184 over 4. We want to try and find perfect squares in here, and we'll be able to find that this is equal to 12 plus or minus the square root of 4 times 46. 46 is 2 times 23. Both of those don't have a perfect square. So we're going to divide by 4. We're going to split the rational. So we're going to have square root of 4 times square root of 46. Square root of 4 is 2. So now we have 12 plus or minus 2 times square root of 46. And we're going to put this all over 4. We could divide by 2 by each of these coefficients. So we're going to have 6 plus or minus square root 46 over 2. Now, what this means is x is equal to 2 different solutions. We have x is equal to 6 plus square root 46 all over 2, or x equals 6 minus square root 46 all over 2. And this would be our final answer. If we just had this equal to x, this technically isn't wrong, but we want to ensure that we know that we didn't find one solution, we found 2 solutions. That's why I'm splitting them to emphasize that fact. Huh. And that is the quadratic formula. We could also solve through factoring, and that we will use our previous rules. So where you can find different ways to factor it. I will cover that more in office hours. So with a little bit of exposition, if you have x squared plus 3x minus, let's do 4. What I could mark this as going, okay, how do I get this? There are many different ways to try and figure this out. If you do not know how to factor, use the quadratic equation. If you do know how to factor, then, or you're kind of hesitant, talk to me during office hours, but it looks something like this. I want an x squared. So I'm going to form 2 binomials. I'm going to put an x and an x here because x times x is x squared. And now I'm going to be looking at this last term, and I'm going to say, okay, -4. How can I get a -4? Well, I need 1 to be a minus, 1 to be a plus, because I'm going to be timesing a negative to a positive. Because if I had 2 negatives, well, that'd be a positive. And if I had 2 positives, well, that's positive. So now I want a factor of this that they'll add to this +3. So maybe I'll try 4 and 1. Well, -4 times +1 is certainly -4, but when I distribute this, I'm going to get a -4x, and here I'm going to get a positive x, so I'm going to get -3x. So that would be wrong. However, I got a -3x. So let's try switching the sign, and I end up finding that this is equal to x minus 1 times x plus 4. And that's my solution. So in this case, if we had this being all equal to 0, I then have x equaling 1 or -4. Those are my solutions, because if I plug in 1 to here, I make this 0. 0 times anything is 0. And if I plug in -4 here, I get 0. Well, 0 times anything is 0. So that's a quicker way to find a solution if we're able to factor it. In this example, I'm not going to factor that. If you can factor that, way to go. But when in doubt, use the quadratic formula. It'll get you where you want to go. Okay. So the last section of the topics that we want to cover is matrices. So addition and subtraction of matrices. It works almost exactly how you would think it would. If I have 1, 2, 3, 4, and I'm going to subtract the matrix, let's do 2, 3, let's do 1 and 0. I just align the columns together and I say, or the entries together, and I say, what's 1 minus 2? Well, so I'm going to write 1 minus 2 here. 2 minus 3. I'm going to have 2 minus 3 in the top right entry. 3 minus 1. 3 minus 1. 4 minus 0. 4 minus 0. And when I solve for my next step, I'm going to get -1, -1, 2, and 4. That's the resulting matrix. Now, same thing with real numbers. If I take these two matrices and I switch them, well, I'm subtracting here, so I can't just do that. I'll get a wrong answer. However, with addition, I can switch them and I'll get the right answer. Now, if we look into matrix multiplication, that's where things get a little bit different. So let's try 1, 2, 3, 4 times matrix 2, 3, 1, 0. And so how we do this is you take the top column and you times it by, or sorry, the top row and times it by the first column. That's going to get your top right entry. So think about, I'm taking my first row times my first column. That's going to get me my first column, first row entry. And so when I do that, I'm going to have 1 times 2 plus 2 times 1. Now, when I take my first row and times it by my second column, that's going to get my first row, second column entry, and it'll look something like this. 1 times 3, 1 times 3, plus, and now we have 2 times 0, 2 times 0. For the next one, we're going to have now the second row times the first column. So that's going to be a second row, first entry. So we're going to get 3 times 2 plus 4 times 1. 3 times 2 plus 4 times 1. And now the second row will be times by the second column. So we're going to get the second row, second column entry. 3 times 3 is 9. 4 times 0 is 0. So I'm going to write that as 3 times 3 plus 4 times 0. make my simplifications. And for the top right number, I have 2 plus 2. So that's 4. 3 plus 0. So that's 3. For the bottom row, I have 6 plus 4. That is 10. And for this row, we have 9 plus 0, which is 9. Now, it is extremely important that matrix multiplication is not commutative. Matrix multiplication is not commutative. Let's verify that here. If I have 2, 3, 1, 0 times 1, 2, 3, 4, what do I get? I'm going to have 2 times 1 plus 3 times 3. Then I'm going to have 2 times 2 plus 3 times 4. Now I have 1 times 1 plus 3 times 0, and then 2 times 1 plus 4 times 0. And I get a resulting matrix of 9 plus 2, that's 11. 4 plus 12, that is 16. 1 plus 0, that's 2. And 2 plus 0, that is 2. Not equal. So just by switching the matrices, they're not confirmed to be equal. So the only time that I can guarantee this being true, that we could switch them, is when we have the matrix 1, 0, 0, 1. When I say that, I mean, when I say 1, 0, 0, 1, I'm talking about 1, 0, 0, 1. So whenever I read out the matrix entries, I'm reading it from the top row, left to right, followed by the second row, left to right, and so on and so forth. This is known as the identity matrix. So what's important about the identity matrix is that it allows you to it's a guarantee that I can times by it and not change the system. But if I can times one matrix by another matrix and it results in 1, 0, 0, 1, I know that that matrix has an inverse. Because unlike the real numbers, whenever I have a real number besides 0, I have an inverse. We can think of that as, like, if I have 4, I can divide by 4 and I can get 1. That's not always the case with the matrix. You can't always get back to the identity. And so we need to know, 1, how to find an inverse matrix, and then 2, verify that it's an inverse matrix. But to do that, we first need to know about determinant. So a determinant of a 2 by 2 is found through the equation. I'm going to set A to equal A, B, C, D. So I'm saying that the entries are A, B, C, D, and they're all real numbers. The determinant of A, signified by DET with whatever matrix you have in there, is equal to AD minus BC. So you can think of it, I'm going to take the diagonal, AB, I'm going to times that and subtract the other diagonal, BC. This works for a 2 by 2 matrix. We won't be going further than 2 by 2, so don't worry about finding the inverse for like a 3 by 3 or anything higher than that. And so, as an example, if I have A equaling 1, 2, negative 3, 10, the determinant of A is equal to 1 times 10 minus negative 3 times 2, which is equal to 10. This is negative 6 times the negative 1. So I have 10 plus 6 as 16. So the determinant of A equals 16. So my determinant is non-zero. So very important that if determinant, or sorry, let me just say the determinant of A does not equal 0 implies that A has an inverse. As well as if A has an inverse, that means that the determinant of it must not be equal to 0. In a similar fashion, determinant of A is equal to 0 if and only if A does not have an inverse. And this arrow here is if and only if, meaning that it works both directions. So if it does not have an inverse, the determinant is equal to 0. If it has an inverse, the determinant is not equal to 0. If the determinant of a matrix is 0, it does not have an inverse. And similarly, if the determinant is not 0, it has an inverse. How can we state this so confidently? Well, through the inverse formula. A inverse, so I'm going to write A to the negative first, that is the inverse of A, is equal to 1 over the determinant of A times, and we're going to swap the central diagonal, so we're going to put D here and A here, and now we're going to take the negative B and negative C. Okay. And so before we calculate this, I want to cover scalars real quick, and then we will find the inverse of this matrix here. Let me swap these real quick. Okay, so when I have a scalar, what I'm talking about for a matrix is something that is times by. So if I have 3 times by 1, 0, 2, -3. This 3 is timesing this matrix. I'm going to take this 3, I'm going to times by every entry in the matrix. So I'm going to have 3 times 1, 3 times 0, 3 times 2, and 3 times -3. And the resulting matrix is 3, 0, 6, -9. And as you can imagine, it works in the reverse direction too. I can divide each matrix by 3. So I can take the 3 out of the matrix entirely. Okay. And this works for anything. So if I have alpha of A, B, C, D, alpha is a scalar. I'm going to have alpha times A, alpha times B, alpha times C, and alpha times D. Okay. So now, going back to finding the inverse, we've already found the determinant of this matrix A being 1, 2, -3, 10. We already found that the determinant of A is equal to 16. So now we're going to set up this formula. So A inverse is equal to, and we're going to write 1 over 16 times, we're going to swap A and D. So 10 goes here, 1 goes here. We're going to take the negative of entry B and C. So we have -2 for the top right and +3 for the bottom left. And we can distribute the 16 to get 10/16, which reduces to 5/8 minus 1/8 for entry B. And we have 3/16 for entry C and 1/16 for entry D, or the bottom right entry. Okay, now we want to verify that this is actually a inverse. So let's take A minus 1, or A to the negative first, or A inverse, I should say, A times A inverse. And I'm going to have 1, 2, -3, 10 times 5/8, -1/8, 3/16, and 1/16. And when I do the matrix multiplication, I have 5/8 times 6/16, or sorry, 5/8 plus 6/16, or 2 times 3/16. Where for the next entry, we have -1/8 plus 2/16. Now we're going to have -3 times 5/8, so that is -15/8. And in the bottom entry, we're going to have +30/16. And for the last entry, we're going to have -3 times -8, or -1/8, so that is 3/8, plus we're going to have 10 times 16, so that's 10/16. And when we reduce the fractions and combine them, we have 5/8 plus 3/8, so that's 8/8, which is 1. -1/8 divided by 2 or plus 2/16. That's same as 1/8. So -1/8 plus 1/8 is 0. And -15/8 plus 30/16 is -15/8 plus 15/8, which is 0. And finally, 3/8 plus 5/8, when we reduce that fraction, gets us 8/8, which is equal to 1. So it is an inverse. Okay. That is the review. If you have any questions, comments, or concerns about any of this material that we reviewed, please come to my office hours or send me an email. Office hours, again, are posted in the syllabus as well as on the Canvas page. For the check your learning this week, I want you to respond, write down the question and respond to this question, which is matrix multiplication commutative? True or false? I'll say again, is matrix multiplication commutative? True or false? That will be your check your learning assignment this week for your participation grade. And as a reminder, combine all of those throughout the entire week and submit them as one PDF at the end of the week. Thank you and have a great day.